Can I start?
Hello, everybody. Welcome to today's current seminar. Today we have two speakers and two talks. Our first speaker is Chuanqi Chen. He will be giving a talk on conditional Gaussian Koopman network for modeling complex systems and efficient data assimilation. Chuanqi Chen is a PhD candidate in mechanical engineering at the University of Wisconsin-Madison, advised by Professor Jin-Long Hu, and is expected to graduate in May 2026. He received his master's in industrial and systems engineering from the Georgia Institute of Technology and his bachelor's degree in statistics from the University of Illinois Urbana-Champaign. His research focuses on scientific machine learning, uncertainty quantification, and data assimilation for modeling and simulation of complex dynamical systems, chaotic, multi-scale, and stochastic. With that short introduction, the floor is yours and you can start your presentation.
Okay. Thanks for the kind introduction. So today's my topic is the scientific machine learning for modeling, filtering, and forecasting complex dynamical systems. And we propose a novel neural network architectures called Conditional Gaussian Koopman Network to do this. So first of all, let me introduce what is the complex dynamical systems. They are ubiquitous in many scientific and engineering areas. They are characterized by those very complex behaviors, such as the nonlinearity, high dimension, multi-scale features, and etc. As some examples, real examples, ocean circulation, heat transfer, and cell dynamics. To describe those complex dynamical systems, we usually have two types of models, physics-based models and data-driven models. The physics-based models are usually described by the differential equations, ODEs, PDEs, and they are stochastic variants. For the data-driven models, nowadays people are using the machine learning models. However, in real applications, the data of the full system state are typically not available. So this will make the complex dynamical systems become partially observed. And here becomes the motivation of today's talk. We want to build a digital twin for partially observed complex dynamical systems, and we want to overcome the uncertainties arise from three sources. First is the intrinsic stochasticity. This is the dynamics noise. Second is the chaos and turbulence. This is also the system properties. The third one is the noisy and partial observations, which means that when we collect the data, there are some noise in our measurements. The third one is that nowadays we are still lack of an analysis tools to efficiently and accurately estimate the system states. So to overcome all of those difficulties, we propose a unified deep learning framework to facilitate the state forecast, data assimilation, uncertainty quantifications for partially observed complex dynamical systems. And a very classical examples here is the Apollo program. The problems here is to navigate a spacecraft from Earth to Moon. And to do so, they combining the dynamical models with the noisy observations to estimate the position and the velocity of those spacecrafts. And everything will run on board in real time. And the storage for the computer is only 2 KB. So in these kind of problems, they use the Kalman filter, which is a online learning framework to gradually calibrate the estimations for the trajectory of the spacecraft. And the success of the Apollo program also inspires some other following projects, such as the aerospace navigations, GPS, radar tracking, robotics, and modern data simulations, especially in ocean and aerospace applications. And here is a very brief introduction for data assimilation. Data assimilation is the process of obtaining the best stochastic estimate for system states from the observations of the complex dynamical systems. It can be written in these high-level equations. The model with data, we can get the estimated states. The model can be biased and have some uncertainties, and the data is allowed to condense noise. The model is in this form. This is a stochastic differential equations form. with the U be the observed variable, and I think the U is the observed variable and V is the unobserved one. The goal here is to using the data of the U to infer the V. And here is the process. Each time when we observe a data, for example, U at time 0, at time t0, based on these observations, we can estimate the probability density functions, conditional probability density functions of the V0 given U0. And this one is our state estimates for the unobserved states V. Then we observe a new data U at the time t1. We assimilate these new observations into our previous conditional probability density functions to update the V1 given the U0 and the U1. And the whole process is keep going. Each time when we have a new observations, we assimilate it into our previous estimates. This is the so-called filtering. And for each filter step, it contains two sub-steps. Prediction step, it is also called the forecast step, and the analysis step. One of the filter is the conditional Gaussian filter, which is proposed by the Professor Chen and his advisor Andrew Maeda. The well-known Koopman filter is one special case of this conditional Gaussian filter, CG filter. So let's consider a type of stochastic differential equations, which is called conditional Gaussian nonlinear systems, CGNS for short. The U is observed states and V is the unobserved states. So this kind of CGNS is following some special structures. That is, the unobserved states V appears linearly into these systems, while the U variable, the observed states, can be arbitrarily nonlinear. And the nonlinearity is wrapped by the functions f1, g1, f2, g2. So those four functions can be arbitrarily nonlinear, and it provides the nonlinearity of the U into the systems. However, the V can only be linear. The problems here, or the goal here, is to, given the data of the U, we want to infer the states of the V. There are many methods can do this, especially the Koopman family filters, ensemble Koopman filter, expanded Koopman filter, and so on. And all of those filters are based on the Bayesian inference. So,
Hi. Sorry, I have a question here.
yes,
Are these filters in some sense related to the filtration of the sigma algebras?
the Apollo programs, they are using the original Koopman filter.
Right. But this is in some sense, whatever I know, corresponding to U1, V1 is predicted based on the information I have up till time T1. So T0, T1. So for Vn, I'm predicting Vn based on, in some sense, based on the information I have from U0 up to Un.
Yes.
And you're calling this as a filter, is that correct?
Yes.
Okay.
So there are two different forms of the filter. One is based on the state space model, SSM for short. And this one is more dynamical systems way. This is the so-called partially observed dynamical systems. Basically, they are interchangeable. The original Koopman filter is based on the state space model. Yes, that's just a very, yes. To do so, let's get back to the goal of this data assimilation task. Given the data of the U, we want to infer the unobserved states of the V. We have some filters to do so, but based on the spatial structures of the CGNS, we have the analytical formulas to do so, which we call conditional Gaussian filter, CG filter in short. As I explained before, the goal is to estimate this conditional probability density function, Vn, given the history of the U here, U0 to Un, and we want to estimate the Vn. Based on this spatial structure, or utilizing this spatial structure, this conditional probability density function is Gaussian. And the mean and the covariance of these Gaussian distributions their evolutions can be expressed by these analytical formulas. By solving these U equations, mu equations, and the covariance equations, we can solve for the conditional PDF of this U variable given V variable given U variable. And this is very similar to the Koopman filter, with the K here can be treated as the Koopman gain. So this computational cost for solving those two equations is the cubic n to the 3. However, if we utilize some other popular methods, the ensemble methods, for example, ensemble Koopman filter, for example, we may suffer from the curse of dimensionality because this is a Monte Carlo-based simulation methods. The computational cost will grow exponentially. So the motivation of this project is that when our Koopman equations or when the underlying dynamics does not have this spatial form, which means that we also have the arbitrary nonlinearity of the V, we still want to use this analytical formula. We do not want to rely on some Monte Carlo-based methods to handling the nonlinearity or the non-Gaussian phenomenon. So we want to transform this exponential growth to the cubic growth, polynomial growth, basically. And here is a quick note. Although this is exponential growth, the ensemble size, we can still choose a very small one, but this will introduce some sampling error. And another prerequisite for this today's topic is Koopman operator, which we use it to linearizing the nonlinear dynamics. Consider this nonlinear dynamics in the general form with the F be nonlinear. We can use the Koopman operator to make the nonlinear dynamics become linear. We can add observation functions at the both sides. We add, for example, the J is observation functions on both sides, and we define this composition of the functions as the Koopman operator. So it will transform nonlinear dynamics to linear dynamics. To use this Koopman operator, we build the data-driven Koopman operators, which is learned from the data. We try to learn a finite approximation of the Koopman operator because by theory, we do not know what the F is. We want to use it computationally. In real practice, we will transform this nonlinear dynamics to this linear one with the K be a matrix. K is a linear operator, a matrix. And phi is the decoder, is the encoder, the encoder. We encode the original states X into the Y and turn this Y into linear dynamics. Then we decode the result back by a decoder psi. So we can evolving the dynamics linearly into this Y space and then decode the results back to the X space. There are many methods of the data-driven Koopman operators, such as DMD, eDMD, and the deep learning-based method. The right-hand side panel shows the process, the visualizations of the process. Then comes to our method. So the whole idea of this project is that we want to use this Koopman operator for transforming any arbitrary nonlinear dynamics into this conditional Gaussian forms, such that the V appears linearly. So that's the connections between the CGKN and the Koopman. Why we want to use the Koopman in these cases? Because it can linearize something. So consider this nonlinear dynamical systems, where the observed states and unobserved states, they are coupling with each other in any arbitrary nonlinear way. So we can find that the arrows shows that they are nonlinear. Then we use a generalized Koopman theory. We only linearize the unobserved states. We retain all the nonlinearity of the observed states. So it will transform the systems into this CG system. And the states is they call the CG state. We retain all the nonlinearities of the observed state. The observed state is retained, but the unobserved state is transformed into the latent state. And the latent state appears linearly into these new systems. And we call it conditional linear. Then in these conditional Gaussian systems, we perform the predictions, which is solving initial value problems or doing the time series forecasting. In discrete case, we use the state transition. In continuous cases, we solve the differential equations. And then when we get the results, when we get the predictive results, we decode the results to the original systems because all the states of interest are in the original systems. We do not care. We do not want to know the later states finally. Then is the data assimilation process. The data assimilation is that since we have a conditional Gaussian systems and we have the latent state appears linearly, we can use the CG filter. We first use the observed state, infer the latent state, and then decode the latent state back to the unobserved state. Because these systems has the conditional Gaussian form, we can use the analytical formulas, which will boost the data assimilation performance and allow us to avoid using the Monte Carlo-based simulations. Here is the mathematical descriptions of this process. Consider we have a general complex dynamical systems in an arbitrary nonlinear way. Here, G is a nonlinear dynamical systems. So U1 is observed states, U2 is unobserved states. We can equivalently rewrite these equations into G1 and G2. These two are equivalent. We linearize the U2. We use the basis functions phi here. Here, phi is the neural networks. We transform the U2 into the V. V is latent state. And we reorganize the U1 and V into a new systems. Here, the V appears linearly into the systems, while the U1 can still be arbitrary nonlinear. And the nonlinearities is wrapped by F1, G1, F2, G2. In this new these nonlinear functions, F1, G1, F2, G2, and the encoder phi, they are all neural networks. So we call this neural CGNS because all the dynamical functions are parameterized by the neural networks. In this neural CGNS, we perform the state forecast and efficient data assimilation. At last, we transform all the results back with the decoder psi. And this process is the generalized Koopman theory. A quick note here is that the true governing equations, G here, G1 or G2, we do not require them to be known. So those true governing equations is not required. All the 6 components, F1, G1, F2, G2, and encoder phi, decoder psi, they are all learned from the data. The data is the time series data of the complex dynamical systems, the time series of the U, basically. From the time series of the U, we learn the 6 components from optimization algorithms. And everything here is handled by the Conditional Gaussian Koopman Network, CGKN. And this is the architectures of the CGKN. Panel A shows the processes that I have explained, and we make transformations between arbitrary nonlinear dynamical systems to the dynamical systems contains the conditional linear structures. We do this by the Koopman theory, or a generalized usage of Koopman operator. Panel B shows the architectures of the CGKN, how we implement these processes. It consists 2 parts. First is the eta. The eta is just a straightforward neural networks. It will output 4 components, F1, G1, F2, G2. Here is their positions. Of course, we can use 4 different networks for each of them. But sometimes, or typically, we can organize them together with a single neural networks eta. They are the same. The second part is the autoencoder. We implement the decoder and the encoder, psi and phi, into autoencoder architectures. Here I split them, but sometimes the illustrations will connect them together. They are just the autoencoder. I split them for the illustrations of the data assimilation and the state forecast. With the outputs of the F1, G1, F2, G2, these are the dynamics terms. And with the U2 with the V variable, the latent variables, we can have all the states of CG states. And then we can do the state forecast. We can predict the future states with these state transitions equations. And with the data of the U1, we can do the data assimilation. We can find that the data assimilation only relies on the U1. There is no errors that get from the U2 here. Given U1, we can use the CGKN to perform the data assimilation. We can get the mean estimates and covariance estimates for the V variable. At last, we decode those estimates back to the original U2 variable. So the decoder, yes.
Hi, sorry, I have another question is, when you're trying to do data assimilation, you get a covariance matrix as well as a mean one, right?
Yes.
And then, what is R?
The R is posterior covariance.
Oh, I see.
Yes.
Okay.
Mu
Thank you.
is posterior mean, R is posterior covariance. Yeah. So here is the data assimilation processes. For the state forecast processes, we will just have the predictive states at the future time, n+1, given the data at n. So state forecast is very straightforward. This is just a time series forecasting or IVP problem. Panel C shows the real examples of the Navier-Stokes equations. Assume that we have a 2D Navier-Stokes equations, a 2D turbulence. What we can observe is only the sparse observations on this spatial domain. For example, we can only observe the 8x8 sparse positions in this continuous field. And given this time series, given the history of these sparse observations, we can use the CGKN to recover the most current state at the Tn. We can recover the continuous field. And based on this recovered field, we can then make the predictions in the future. So this is two steps, but CGKN can do the two steps in one shot, in one model. This is the continuous version of the CGKN. So previous one, I showed the discrete one. Discrete one basically is discrete in time. We have a state transition operator here. For the continuous one, it is the in a differential equation form, in a dynamics form, but basically that's the same. Panel B and panel C shows the nodes, the graph nodes of the process. The state forecast is that given any initial conditions, we first encoded the unobserved states into latent states, and in this latent space, we make predictions. And last, we decoded the results back. For the data simulations, given the U1 data, we first estimate the latent state V data, and then we decode the V data to the U2 data. And this is the inference of the CGKN. Given the model of the CGKN, what kind of inference we can do? First is the data assimilation. Given the data of the U1, which is the observed states, the time series data, we can use the analytical formulas here for estimates, the mean, the posterior mean mu V, and the covariance V of the V variable here. And at last, we decode the mean of the V back to mean of U2 by the decoder psi. And I
had a quick question.
Yes.
Yeah, so when you say Koopman network, are you referring to F1 G1 and F2 G2? So are those the parameters which are forming the Koopman network when you refer to as the Koopman network?
So for the Koopman network, I mean the autoencoder. I mean this part.
Okay.
I mean the transformation between U2 and the V.
Okay. And
Yes.
then what is the eta referring to? So what is that part referred to as?
The eta means the dynamics. So here we can find that we transform the original nonlinear systems to these conditional linear systems.
Right.
But F1 G1, so we retain all the nonlinearity of the U1, and we do not know how to express those nonlinearity. We use F1 G1 and F2 G2 we want to use the four terms to express the nonlinearities of U1. But these two terms are the neural networks.
Right.
So we learn the parameters inside the F and G.
Got it. Okay.
Yes.
Thank
But
you.
for the Koopman part, it means that the encoder and decoder processes, we try to find the linear embeddings basically. The linear embeddings is the latent state V, such that U2 is disappeared, such that U2 becomes V, and the V appears linearly.
Right.
Yeah. And
I have a follow-up question following what Rutvik asked.
yes.
So in one of the earlier slides, you said V at a later time step is the Koopman operator operated n times on V at the initial time steps. It was like, I think in slide 4 you mentioned that.
Is this one?
Sorry, maybe slide 5. I'm sorry.
Oh, it's okay. It's okay. No problem. Next one.
It was where you defined the Koopman operator. Yes. So
Yep.
right. So by this, you can say that if you want to go to G at x n plus p time step, you just have to do k power p g of x n, right? So where are you doing the k in your final algorithm? That was what I was wondering.
You mean what is the K in my case?
Yes.
That's
That
a very
you
good
are
question. Yes, that's a good
linearly
question.
enforcing, yeah.
Yes. That's a very good question. So here, the classical usage of the Koopman, we have a matrix K here.
Right. Mm-hmm.
It is
Right.
just
Yes.
it is just a matrix that contains the weights or coefficients, a matrix of coefficients. It does not rely on anything. However, in my cases, my K is a state-dependent term. My K is depend on U1. So here, my K becomes F1, G1, and F2, G2.
Okay, I see. Okay.
Yes.
I understand.
Yeah.
Right.
That's a very good question.
Yeah. So building on top of that, so isn't that K referred to as the Koopman operator? So isn't F1, G1, F2, G2 essentially constructing the Koopman matrix? Or is that not how we interpret it?
Yes, you can interpret it this way. That's a very
Oh.
good viewpoint.
Okay.
So for the implementation of the data-driven Koopman, we have the encoder and decoder process. They are very important. I mean, the transformations between U2 and the V. And as you said, F1, G1, and F2, G2, they are the K in the classical usage of the Koopman. So they are also very important.
Okay, got it. So
Yes.
essentially here, the concatenated UN and VN is forming the YN that we saw in the previous slide, right?
Yes.
Okay, got it.
The Y in previous slides is the V here.
Right. Okay.
But in previous Koopman, we do not have the U1. Because in previous one, the Koopman is trying to linearize the whole systems. And right now, I just want to linearize partial system, part of my system, U2 here. I do not want to do anything to my U1.
Got it. Okay.
Yeah, hi.
Thank you.
I have a follow-up question. So I think the idea of the Koopman operator is to linearize the system. So the Gaussian filter will keep Gaussian, right? So before and after the filter. But here, if it's a conditional linear,
Yes.
can you still have this kind of property?
You mean the Koopman or the DA formulas?
So now the Koopman is like the conditional linear, right? So the system, as you said, you just linearize partial of the system.
Yes.
And I think the idea of the Koopman is to guarantee the distribution will keep Gaussian. So you can use the classical form of the the Gaussian filter, right?
Yes, exactly.
But
so
yeah, my
so
question is, if you're just a linear part of the system, can you still guarantee the Gaussian distribution keeps Gaussian?
That's a very good question. So that's the reason. That's the core reason why we only linearize part of the systems. Because as I mentioned here, our conditional Gaussian nonlinear systems, the CGNS, can allow the nonlinearity of the observed states. So this is our target form. So why we only need to linearize part of my systems? Why we want to transform to these targeted systems? Because this system, this CGNS, can allow the nonlinearity of the U here, the observed states, and it can still has the conditional Gaussian filter.
Okay, so where does this conditional Gaussian nonlinear system come from? So you prove it, or?
Yes, it is proposed by Professor Chen and his advisor Andrew Maeda.
Okay, I see.
Yes.
Okay,
so that's,
thank you.
Yes, so that's why here is I say that Koopman filter is one. Actually, they claim that the Koopman filter is one special case of the conditional Gaussian filter. Yes.
So the Koopman filter will follow strictly the linear dynamics,
Exactly.
but here is
Exactly.
somehow relaxed to
Yes,
partial.
yes.
Yeah. Okay. Thank you so much.
It can allow some nonlinearity, and we use this feature, so it can allow us just to linearize part of the system.
Okay. Okay. Great. Thank you.
And here is I just talked about the architecture and the inference of the data assimilation. Here is the inference of the state forecast. The inference of the state forecast is even more straightforward. As I said, it is just IVP problems or time series forecasting problems. Given the initial condition UN here, we want to predict the states in the future. So we first encode the unobserved states U2 into the latent states V and organize this CG state. In the CG systems, in the neural CG system, we make the predictions. We use this as a state transition operator. We just plug in the current state U1n and Vn. We can just get the U1n plus 1 and V plus 1. At last, we use the decoder psi to decode the V back to U2. Here should be the V. That's the type over here. This term should be the V term. And the next question is that how to learn the CGKN from data. I have just introduced if we have a pre-trained CGKN, how to use the CGKN, how to apply the CGKN in some real practice. But the next question becomes that given the data, given the time series data of the U here, the star means the true data, how we can learn the 6 components, basically. And we propose different loss functions to empower our model and do different things. The first one is the loss of autoencoder, loss AE, which ensures that the encoder and the decoder is invertible, is a correct autoencoder. The second and the third term is LU, LV. They are the forecasted loss of original state, U, and the forecasted loss of the latent state, V. By adding these 2 loss functions, we can ensure a very good state forecast performance. And the last one is the loss of data assimilation. This one is the normal loss that we propose in this work. We given an initial CGKN, we put the data assimilation processes into the differentiable training process. So given when we have an initial model, the DF performance will be very bad. And these processes will be tracked. The gradients of the process will be tracked and will be added into these loss functions. By minimizing these loss functions, our model DA performance will gradually become better and better. And the core reason why we can organize this loss of data assimilation, because we have a very efficient DA process. If we still using the ensemble methods or particle methods, the computational cost cannot be affordable to make it even become differentiable. So here the loss functions has three features. First is empowering DA capability. Second is that it can help us capturing the probabilistic relationships between states. So time series forecasting is trying to capture the probabilistic correlation between time. For example, Tn and Tn plus 1. But this loss of data assimilation help to capture the relationship between states or between spatial correlations, basically. The third one is that because of the second feature, it can mitigate the overfitting. When we do not have enough data, when we add this data assimilation loss, it can help capture some intrinsic probabilistic correlations inside the data. And the optimization algorithms is the additive loss of those four loss functions, a weighted loss, basically. By minimizing this total loss, we can get the optimal parameters inside F1, G1, F2, G2, and encoder phi, decoder psi. So this is the so-called differentiable data assimilation. And I have introduced yes.
Just a question on this slide. So you assume during training you have both the observed and unobserved states, correct?
Yes.
Which is why
yes.
you didn't put a subscript 1 or 2 in the training data.
Exactly.
Correct? Okay, sure. Yeah. Thanks. That's all.
Yes.
That's a clarification. Thank you.
Yes. So this is the offline training process, which means that during the training process, we still need the unobserved data. We still need the whole data of the U. But as long as we have a trained model, when we try to use it or when we try to apply it, only the observed states UI is required. Because the CGKN can do the DA, we can use the DA to recover the unobserved states, and then use the DA recovered unobserved states to make the predictions in the future. There is some examples I can show you.
Thank you.
Yes. The second is that the uncertainty quantifications, because what I have introduced is all about the pointer estimation. It's all about the specific states in the future or data assimilation. Here is the post process to perform the uncertainty quantifications. Basically, we try to estimate the sigma here, the noise coefficients or covariance here. The UQ for state forecast is very straightforward. We just use the RMSE, root mean squared error, to quantify the uncertainties of the predictive states. This is the formulas of RMSE. The second UQ is for data assimilation. This one is more interesting because here we use a technique called the residual analysis. After we have a pre-trained CGKN, sometimes when we have a new observation U1, we can make a good state estimation. Sometimes when we have a kind of bad U1, when our observations is very, very noisy or our observations is not that good, then the update may not be very effective. The update may not be successful. So we want to know what kind of UI is good or bad. So we calculate these deviations or the absolute errors between the true data of the U2. U2 is unobserved states, and the DA estimated mean, mu here. So we can have a series of residual. The residual is defined by the absolute error here. And we build assistant neural networks between U1 and the residual R here. So these neural networks can tell us what kind of U1 will give a very large residual and what kind of U1 can give a very small residual. So based on these neural networks, we can predict the error. And this error is the standard deviations, is the estimated standard deviations of the data assimilation point estimation. And this whole process is a post-process of a pre-trained CGKN. So all the computational cost is training a feed-forward neural network, NN here, which will be very fast. And this is the numerical experiments. We performed some of the numerical experiments for different PDEs, Viscous-Burgers equation, Curry model, Shwasinski equation, and the Navier-Stokes equations. And we have two matrices, the forecast error and the DA error. We benchmark the method CGKN with some other DA methods and the state forecast methods. For the DA methods, we compare it with the ensemble Koopman filter and direct spatial interpolation. For the state forecast, we benchmark it with the DNN, CNN, and the Fourier operator, FNO here. A quick summary here is about why the CGKN can accelerate the DA process. First is it used analytical formulas. We transform arbitrarily nonlinear systems into the CG systems, and that CG system will have the analytical DA formula. The second is that if you remember that we transform the U2 into the V variable over here. When the U2 has very large dimensions, for example, it is continuous cases. It is a continuous spatial domain, and we discretize it into 1024 points. In these cases, we will lower the dimension of the U2. We lower the dimension of the U2 to the V here, which will save the computational cost. So we use these low order representations in our model. This is somehow behaves like the reduced order models, the ROM. And the third one is that we use a coarse-grained map. We do not build maps between states to dynamics. For the PDE problems, for the PDE data assimilation problems, we build maps between states. It is state-to-state map. It is not the state-to-dynamics map. So because of this, we can achieve speed advantages over the classical methods, the ensemble Koopman filter, at least 100 times faster in these three numerical examples. And the future work is that we can still boost the speed by introduce the sparse structures. We can introduce the sparse embeddings. We manually make the embeddings become sparse and utilize that sparse structures to further boost the speed. And this is the numerical examples in the viscous Burgers equations. Here is the Koopman equations and the data simulations process. We simulate 1,000 times for train data and another 1,000 simulations for test data. And in this case, the problem setting is that for the 1D spatial domain, we can only observe 4 points uniformly distributed on this domain. The spatial domain is 0 to 1. And in this 0 to 1 domain, we can only observe the black dots. The black dots is only the data that we can have. So the problem here is that we want to use the 4 black dots to infer the original spatial profile, the original spatial functions, or in this viscous Burgers equation. And here, this figure shows the performance of different data assimilation methods. The red trajectory is the CGKN. We can find that with the time evolving, more and more 4 dots can be observed, and they're simulated into the model. And it will gradually make the red trajectories align well with the truth. The truth is the black. As a very obvious comparison with the green trajectory, which is the interpolation method. The interpolation is that we just connect the 4 dots, because with no other knowledges, what we can do is only use a linear interpolation. The linear interpolation is just to simply connect the 4 dots. We can find if we just simply connect the 4 dots, the performance is very bad. It cannot capture anything about the shock behavior or the trend of the spatial functions. But when we use the data assimilation, it can recover the true black trajectories. The lower panels shows the ensemble Koopman filter process results, which is the blue trajectories. Both of them can match with the truth very well. But the CGKN is much faster. I think it's 600 faster in this case. And here, this is the state forecast process, which is very straightforward. That is, given the initial point, given the time equal to 0, what is the states in the future? And this is the comparisons of the CGKN with the neural network models. And the second example is the Navier-Stokes equations. I have mentioned a little bit before. That is, for this 2D continuous field, we have 8 by 8 sparse observations, same as the 1D cases. For 1D cases, we have 4 points uniformly distributed onto 1D domain. And here, the problems become 2D sparse observations into a 2D spatial domain. Here are the governing equations and the simulation settings. We simulate a single long trajectories, 1,000 time units, and we use the first 800 time units as train data, and the rest 200 time units as test data. Also, we manually add some observational noise to correct the measurements. And this part becomes low order models or reduced order models. Is that our original data? So originally, this 2D spatial domains is discretized into 64 by 64. But the goal here is to use the 8 by 8 to infer the 64 by 64. So the 64 by 64 is my U2. 8 by 8 is my U1. The transformations of the autoencoder is decreasing the dimension. We decrease this 64 by 64 to 16 by 16. So this will saving the computational cost. And with the analytical formulas, the DL performance will, the speed will be boosted. And this is the process. This is the state forecast process. So with the first row be the truth, second is the CGKN. The third is the DN. We find the DN can not capture any useful patterns for the state forecast. I think the best one is still the FNO, the forward neural operator, which is the scientific machine learning models designed for learning infinite learning maps between infinite space. But the CGKN can show some comparable performance with the FNO because they are somehow share the same ideas. The FNO is trying to encode or try to build a models in the Fourier space. The Fourier space is achieved by the Fourier transforms of the original states. So they use the Fourier transform to do the transformations. The CGKN is using the autoencoders to do the transform and build the models onto the latent state. The FNO is build models onto the Fourier states.
Sorry for interrupting you. Can you hear me? Yeah, I think we only have like 10 minutes left.
Okay.
Yeah. And our second speaker is here right now.
Okay.
Thank you so much. If you can go like faster.
Yes, thanks for your reminder. This is the heat map evolutions of the data simulations. The results that we are using the 8 by 8 points to infer the whole field. And this is the results. The interpolations fail to capture anything. It is very blurred. While the CGKN is similar with the ensemble Koopman field, but it is much faster. This is the time series forecast. We fixed one spatial point and track that spatial point along with the time. So we formalize this time series forecasting plot at the position 0.5625. And the last example is the answer problems, the ordinal oscillations. So for the answer patterns, it means the temperature patterns in the Pacific Oceans. If it is warm, it is ordinal. Otherwise, it is linear. So we want to predict the temperatures in the future over the Pacific Ocean. So here is the problems. This is basically become a ODE problem. So SST is sea surface temperature, which is the temperature over the sea, which is observed states because it is not hard to measure. But something is not that easy to observe, which is called a thermocline. This is under the sea, which is very hard to observe. So the problems here is to estimate the edge, the unobserved states server clients based on the observed data. And based on the observed data and the DA inferred unobserved data, we want to forecast the future temperatures. So here is the CGKN formulas. That is, we have the D retained. D is the sea surface temperature. We do not do anything to our observed states U1. So all the U1 states in F1, G1, F2, G2, they are all retained. But all the unobserved states H are compiled or included into the V, which appears linearly into the CGKN. And we train these models by the loss functions I have introduced. And this is the results. The first row is the first one is the PDE simulation, the brand new result. The second one is the constructions from the true states. The third one is the reconstructions from the CGKN, because the original model is a PDE model, but what we build models is on the discrete states. They have some method that can recover the whole field from the discrete states. And this is the final results. And some future applications of the conditional Gaussian Koopman network. First of all is that it can be used to make a try for filtering and predicting 2D turbulence. Yes, I have shown the results of the 2D turbulence. Second one is that it can do the Lagrangian data transformations, which means that when the observed data U1 is the Lagrangian tracer on the sea, for example, the positions, we can infer the velocity field based on the position data. The third one is that we have modeled the non-Markovian systems based on the CGKN. The fourth one is that as the Apollo programs, which is online learning models, so CGKN can be used as an embedded AI into some Internet of Things to do the edge computings. As long as the sensor collects some new data, then the updates can be made on device computing, basically, real-time applications. So overall, if you do not have complete system state data, you may need the CGKN to do the inference. So this is also right now the modern AI or large models cannot do, because they have a lot of parameters, and the inference time is not trivial. It cannot be put on the device to do the edge computing or edge intelligence. CGKN can do it. It is a lightweight model. And that will be all for today's presentation. Thank you all.
Thank you so much. Do we have any questions for the speaker from the audience?
Yes.
Okay.
Hi, Chuanqi. Regarding the Navier-Stokes example,
Yeah.
what was your encoder decoder architecture? Was it like an ML convolutional autoencoder? So but your U1 and U2 are separated. So U1 is the observed states would be the 8x8 points.
Yes.
And the unobserved states would be the entire
field.
Right. Okay.
So somehow we are using U1 to infer itself. We use 8x8 to infer itself, because when we infer the 64x64, it will automatically contain some points that is overlapped with the observed points.
Okay. What about your F1, G1, F2, G2, which are just functions of U1?
The functions of the U1, so they are just simply MLP, I think.
MLPs. So there comes my follow-up question. Like in fluids, very often you track the velocity of a particle, right? You understand so in your case, at all time steps, the position of the U1 was fixed in space.
Yes.
Would you be able to have what if it has to move in time? Position of U1 sensor changes. Like it's not the equispaced 8x8 grid. It could vary in time then.
Yes, I think this is the so-called like ranging data assimilation. Yeah,
Oh, right. For the
yes,
future work. Sorry, yeah, I see. But yeah, thank you. Great talk. Thank you
that's a
for your
good
talk.
question.
It's very interesting.
Thanks.
Do we have any other questions? Yes.
Yeah, I
Can you
have.
introduce yourself
Sure.
first?
Yeah, I have one final question. Yeah, hi, I'm Rutvik. I'm also a PhD student here at Brown, supervised by George Kaniadakis. My question goes back to the loss function formulation. Like, uh, you have a term where you're computing like the MSE for the U, and you have an additional loss term which computes it for V, right? So my question is, aren't we like implicitly imposing a condition on V when you're like minimizing the MSE of U? Because when you're saying U, what I understand is you have like both the concatenated U1 and U2, and then V is essentially a projection of U2 into the latent space, right?
Yes.
So minimizing the MSE of U, wouldn't that in a way reduce the MSE of V also? So why are you additionally
Yes.
imposing that as an additional constraint?
Oh, that's a very good question. That's a very, very good question because based on my experience, that when we want to do continual forecasting in later states, because sometimes we are not only satisfied with one step predictions. When we want to do multiple state predictions, we need to do multiple predictions inside the latent space. So if we do not add that constraints, it will make the multiple state predictions fail.
Got it. Okay.
Yes.
Okay. So this is something that you have observed empirically, is it?
Yes. Yes.
Got it. Okay.
Our second speaker is Yulun Wu. He will be giving a talk on iterative training of physics-informed neural networks with Fourier-enhanced features. Yulun Wu is a master's student and research engineer at KTH Royal Institute of Technology. He will start his PhD at the Division of Decision and Control System of KTH Royal Institute of Technology, supervised by Assistant Professor Matthew Baru and Professor Karl-Henrik Johansson. His research focuses on physics-informed neural networks. With that short introduction, the floor is yours and you can start your presentation.
Okay, thank you. Hello everyone, I'm Yulun Wu, and I'm very glad to share with you our recent paper, Iterative Training of Physics-Informed Neural Networks with Fourier-enhanced features. So this paper focused on solving high frequency PDEs using physics-informed neural networks. So in real life, physics laws govern every aspect of our world. So among them, high frequency systems represents a common but highly complex class of problems. These systems are primarily characterized by the rapid oscillations, rapid fluctuations across both spatial and temporal dimensions, which pose a significant challenge for traditional method like traditional numerical method and machine learning method to approximate, like the interference pattern of the water waves, the smoke convection trails of jets, and the diffusion in the ink dropping into the water. Next, I will introduce pins shortly. So pins are a class of machine learning method that embed physics laws directly into the loss function to approximate physical systems, thereby reducing dependence on labeled data and transform the neural network from a pure black box into a system that governed by the physics principles, physics equations. So for PDE system, we have the general form of the PDE and the boundary condition like this. And taking the 2D Helmholtz equation shown here as an example, while traditional deep learning requires massive data set for training the network, pins only need to sample a small numbers of data point on the boundary of the domain commonly, and with a large set of physics point in the interior of the domain just need to follow the governing equation, but we don't need it to be labeled. From Monte Carlo approximation, the loss function of pins normally consists of two parts of the loss. The first part is the data loss from the labeled data on the boundary, and the physics laws in the interior of the domain, plus the physics weight lambda to balance these two parts of the weight. So for the general workflow of physics-informed neural networks, a standard PINS is a fully connected neural network. During the training process, output like on the boundary condition on the boundary point constitute the data loss, and the outputs at the physics point generate the physics residue through automatic differentiation. So in my perspective, the training process of such a network encompasses of two fundamental tasks. First, as the input data propagates through the hidden layer, the network performs nonlinear feature learning, which each neuron in the last hidden layer can be interpreted as a basis function. Like in the last hidden layer, every neurons can be act as like a basis functions. And in output layer, subsequently, the output layer becomes a linear regression operator to identify the optimal combinations of the coefficient that minimize the overall loss. That in like from functional analyze perspective is the linear projection tasks. So to project the learned features onto the physics state space to form the linear expansion of the solutions. So from my perspective, from traditional numerical method like the finite element method, we notice that the selection of basis functions and the solving of the coefficient are typically decoupled but not coupled. Although the intertwining of these two tasks is an inherent property of the neural network architecture, we think this may not be the best and may not be the most effective way to approximate some complex partial differential systems. So that here comes to our motivations. First, we think standard PINs remain tied to single level optimization framework, where feature learning and coefficient fitting are intertwined in the neural networks. Second, from previous work, we noticed the spectrum bias problem is a very common failure mode in all neural networks. This tells us that the low frequency features are easily to learn. The network naturally prioritizes fitting smooth component first. And for the high frequency features, they are very hard to learn. The network often fails to capture this detailed even after extensive learning process, training epochs. So in the context of PINs, this means the solver tends to capture the general shape of the solution while missing the rapid oscillations essential to the physics. So fail to just capture the high frequency components. And now we can show some common failure mode for PINs, for Vadina PINs for facing the spectrum bias problems. First, let's consider a convection diffusion equation with periodic boundary conditions and the multi-scaled initial conditions like this. So with a low frequency part and the high frequency part. Then the analytical solution for this convection diffusion equations also is also the combination of a low frequency part with a high frequency part. And we can notice that the exact solution for this for the analytic solution for the convection diffusion equations is a smooth, like low frequency part plus with the rapid oscillations in the middle. And during the training process, we can, like from the visualization, we can notice that the neural network, the vanilla pins just failed to capture these high frequency components, but just ignore all of the high frequency part. Another example is for the Helmholtz equations. So if we set the source term like this, then we could have the analytic solution for this Helmholtz equations as sine a1 pi x times sine a2 pi y. So this is the analytic solution for this Helmholtz equations. So if we consider an extremely challenging high frequency case where a1 equals to a2 equals to 100, we want to approximate this solution. Then during the training process, we can notice that during the training process, vanilla pins just fail to converge and fail to give a reasonable approximations. So yeah, so basically, to mitigate the spectrum bias problem, a highly effective strategy is to employ the random Fourier feature mapping. So instead of feeding the raw coordinate directly into the neural networks, we can first pass them through the RFF mapping like this, so that the random Fourier features grounded by the Boucher theorem, they claim that any continuous positive definite and shifting invariant kernels is the Fourier transform of some probability distribution. So random Fourier features gives an implicit expressions of this random Fourier feature map, then approximate these kernels as an inner product constructed through the random sampling using this BD matrix. So basically sample from the Gaussian distribution. So in neural networks, by applying RFF mapping in the input space from the neural tangent kernel NTK theory, the NTK of the network can be converted into a shift invariant kernel where the spectrum domain can be adjusted just by sigma, the frequency bandwidth. So which means like we can effectively control the frequency bands of the network prioritized. A higher sigma, you can consider like you can assume that a higher sigma just stretches the spectrum domain, enabling the network to learn the high frequency component that the standard neural network tends to ignore. So this also works for pins. So now it comes to our the method we propose. We propose IFF pin. This is an algorithm for iterative training of pins with Fourier-enhanced features. So the key idea is to still create feed-forward neural networks with three important components. The first one is we still put the raw coordinate directly into a feed into the MLP to get into the hidden layer to get the nominal basis. So the nominal basis is just the last hidden layer output. So next, we extract this nominal basis and put it in the RFF mapping, this gamma D, to get our RFF extended basis, psi D. And then we use this RFF extended basis to perform the linear regression tasks based on the fixed basis functions. So the key part for IFFP is that the first component and the last component, the basis generation part and the linear regression part can be optimized separately. So the architecture is like a bi-level problem which we can update iteratively. As for the two motivations we stated before, for the nonlinear feature learning, in pins, we use RFF mapping to mitigate the spectrum bias problem. And for the linear regression operator, I would say that our RFF pin is basically focusing on the high frequency linear PDEs. So for linear PDEs, inspired by the optimal control theory, we can make this regression task as an QP problem especially for the linear PDEs. So we can guarantee to get the global optimal combinations of the RFF extended basis as an instantaneous optimal controller that we can get the optimal combination, we can get the optimal coefficient during every training step. So to be more specific, we consider the nonlinear feature learning part as the upper level problem. So before, for vanilla pins, the prediction of the network can be written as U tight equals to W times H omega X, where this W is the projection operator in the output layer of the neural network. And this H omega is the last hidden layer output of the neural network. So this is the vanilla pins, but we want to extract during the training process. We want to just extract the last hidden layer output and put it in the RFF mapping to get our RFF extended basis. Because we can random sample this BD, we have the shape of the BD matrix as like D times P, so that we can, which means that we can extend it the numbers of bases from just P neurons in the last hidden layer to 2D basis functions with arbitrary numbers of D. And here is the structure of the upper level problem. And in the lower level problem, we want to do the linear regression operator. So inspired by the basis function approximation for partial differential equations, we approximate the solution using the RFF extended basis from the upper level problem we get. And this theta is just the coefficient vector for the basis functions. If we bring it back into the Pin's laws we stated before, especially for the linear PDE, we can get a QP problem with respect to theta. So this is a key part of our algorithm. Only for linear PDEs, we can get a QP problem with respect to theta, which means that by Cholesky factorization, we can get the global closed form of the optimal theta very fast, like this. Theta star equals to inverse of Q matrix times C matrix. So here we can consider this theta star just as the optimal controller that we can get very fast in every training step. And here is the structure of the lower level problem. Then the global bi-level problem is like this. So in in every epoch, we first fix the network parameter omega and use the current RFF extended basis to get theta star in the lower level problem. And then we fix this theta to update the parameter omega again. So we not only decouple these two tasks that vanilla Pins is doing, but we consider the theta star as an like optimal controller that we can get the global optimal coefficient in every step, in every training step. Also, the upper level problem, since we are still using the neural network to update the network parameter, so that we can combine our upper level problem with different advanced training strategy in Pins, like different reweighting strategy to enhance the performance. And here is the whole FF Pin algorithm look like. So first, from the input, we put it in the hidden layer, we put in a neural network, and we extract the last hidden layer, we extract the nominal basis to put it in the RFF mapping to get our RFF extended basis, and then we approximate the prediction using the basis function approximation, and then first we fix the network parameter to get our theta star, and then fix star to get to update our network parameter omega. And next we want to talk about some like nonlinear extensions. So for nonlinear
I have a
PDEs,
question. So can I ask a question?
Yeah, sure.
So in the what you call the lower problem, the lower level, so you do that through least squares, right?
Yeah, least squares.
Okay.
So this is the like original Pin's laws.
Yeah, I mean people have done that before, like Natrask and Sandia people, except they didn't have they didn't inject the Fourier features at the last layer. Yeah.
Yeah, we want to use the Fourier features just because we want to like first our first thought is like we want to extend it the basis so that we believe that the bigger the space our basis functions can span, we can get a better like approximation.
Sure.
So that's why, yeah.
Yep.
And for the nonlinear extension, the problem is that now the lower level problem is no longer a QP problem with respect to theta, or like it's no longer convex. So that we need to do some pre-training method to get some good initialization for theta and omega. I think this point is very important. So we propose a very straightforward end-to-end pre-training method, which is like very simple, that we just do the joint update for both theta and omega in the early training step for the training process, which means like during the early training step, we don't do the iterative training, but just do the joint update for both theta and sigma for like some training epochs. And after that, we can turn it back into we can turn the joint update back into the iterative update. But now for the lower level update, we can only use some like gradient descent method just to find some local minimizer, but not the global minimizer, because the problem is no longer convex for theta. But experimental result still shows that under some like nonlinear, even under some nonlinear cases, the method can still be comparable to like all baselines method. So next, I want to talk about some of the theoretical analysis we have made. First is about the convergence analysis for the algorithm. We first want to show that the optimal solution map, this theta star with respect to the network parameter omega, is Lipschitz continuous, so that we can ensure a well-defined Lipschitz hypergradient for the gradient descent on the upper level. So we made some assumptions, but all assumptions we made for the proposition can be easily verified for for example, the lower level problem is a convex QP problem. This Q omega and C omega with respect to omega are locally Lipschitz continuous because of the activation we choose. So it can be easily verified. And also the smallest eigenvalue of Q is above 0 because Q is positive definite. And even for nonlinear cases, this proposition can also be verified as long as we can find a local minimizer of the lower level problem. We can ensure like we always find the local minimizer, and we can prove that the local minimizer retains Lipschitz continuous and differentiable in a neighborhood of sigma of omega. So based on the proposition above, we can prove that the whole algorithm can always converge. The whole algorithm, or like the upper level problem, can always converge to a stationary point for both linear and nonlinear case. Here we complete the proof based on the linear case. So we still have some very easy like assumptions, like Q and C are continuous differentiable. The loss function for the upper level is continuous differentiable with respect to theta and omega. Like the lower level problem is strongly convex, and we need the upper level loss function is bounded below and is hypergradient. This is L smooth. So that we prove the convergence for this for our algorithm. And the second important theoretical analysis is about the expressive capabilities. So at first, the primary reason, like why we want to extend the nominal basis from the last hidden layer, is because that like we believe that because we want to do the basis function approximation for the PDEs. So we believe that the larger space that the basis function space can span, the better approximation result we can have. So we define this two function space HF, the feature space HF, and the composite RFF function space HRFF. So these are the space spanned by the neural network and the space spanned by the RFF extended basis. And we define the projection error like this, so that we want to make the comparison of the projection error of the neural networks versus the RFF extended basis. We want to prove that okay, RFF embedding offers approximation capabilities that are not worse than the original feature space. And this proof is based on the composition kernel theory. So since like random Fourier feature theory is based on the RFF mapping on single X, but our RFF pin use RFF mapping on the last hidden layer on the nominal basis H omega. So we just follow the RFF theory and the properties of the composition kernel to prove that this feature space HF is a subset of the closure of the composite RFF function space HRFF. So we prove that this HF is a subset of the closure of the HRFF so that we can complete the proof. So the proof shows, this theorem too shows that the projection error of the RFF extended basis is always less than or at least does not exceed the projection error obtained from the feature space of the neural network. And in practice, we can almost get better expressivity capabilities for the RFF extended basis than the neural network. And then we want to talk about the experiment part of our paper. So we basically have 5 baselines method and 2 variations of our method. The first is the vanilla pins. The second is the pins formers. This is the transformer-based network architecture. The third one is the neural tangent kernel NGK method. So this is a reweighting strategy by doing the gradient normalization of both the data loss and the physics loss. And the fourth one is the physics-informed Gaussians, this PIG method. They use learnable Gaussian features embedding with the neural networks. So this is a SOTA method, recent SOTA method. And the last baseline is the multiple Fourier features, the MFF method. So this is another like Fourier RFF mapping method directly into the input space combined with the pins. And we have 2 variations of ours. The first one is IFF pin, and the second one is the IFF with primal dual reweighting strategy. So we gradually increase the physics weight during the upper level training so that to have like better approximation. And moving on to the performance evaluation, we first evaluate our proposed method against all selected baselines on several popular benchmark problems. So the first case study involves fitting a low frequency Helmholtz equation. The exact solution is shown in the top right, and the first row at the bottom means the prediction for all baselines in our method, and the second and the second row is the is a log scale absolute error map. In this error map, we can notice that the darker the region indicate the lower error levels. So this representing better fitting accuracy. So it's evident that our IFF method significantly outperforms all baselines, such as like vanilla pins, pins formers, and then NTK approach. And when integrated with the primal dual strategy, the IFF primal dual variant achieves a better performance than the current SOTA method, this PIG, very clearly. Then we can show the visualization for the training process of IFFP in this case study. So it can be observed that our algorithm require only around 1,000 epochs to reduce the error to the orders of 10 to the -3, so which is very fast. And the second benchmark focused on a relatively low frequency convection equation. So the convection equation is a fundamental model describing how a physical quantity is transported through the space over time. So in this case study, we select a relative low frequency case with beta equals to 50. So IFFP and its variants continues to demonstrate a clearly advantage over all other baselines. So looking at the error magnitude, our approach outperforms current SOTA method, this PIG method, over an order of magnitude we can notice. So although IFFP was originally designed to tackle the challenge of high-frequency linear PDEs, this experiment highlights its effectiveness for some common low-frequency problems. And also, we present the result for one nonlinear equations for the Burgers equations. So this is the only nonlinear benchmark in our study. As illustrated in the fitting results in error map, I mean, like even within the nonlinear cases, our FF method and its variance achieves still like competitive performance than all baselines, I would say. And here, the following results are derived from like 5 independent experiments for each baselines across 3 popular benchmark PDEs above, with the red value indicating the average relative L2 error. So it's evident that IFFP demonstrates significant superior performance on, especially on the linear problems for the like Helmholtz and the convection cases. However, it must be like acknowledged that even with the implementation of some pre-training strategies, IFF inevitably encounters local minimum during the optimization for the non-convex lower level problem. So the fitting accuracy for nonlinear case exhibits a noticeable gap compared to the result achieved in the linear cases. So this is some like future works. But next, to evaluate our framework against some challenging spectrum bias issues, we want to investigate some common failure modes for pins, especially focusing on the high frequency and multi-scale problems. So we begin with the Helmholtz equations where the frequency parameter like A1 and A2 are set to like 100 equals to 100. So in this under these conditions, all baselines method fail to get a reasonable approximation. You can notice that. Although some advanced baselines, such as the Pin's formers and this physics-informed Gaussians, they can capture the general shape of the solution. We can notice it captures the shape of the solution. But they remain unable to resolve the high-frequency details. So this failure evidenced by the like very high magnitudes in their error map underscores the limitations of these architectures when facing the rapid physical oscillations. But in contrast, our IFF pin method demonstrates accuracy and robustness. Even in this extreme high frequency cases, it provides a very highly accurate fit like for IFF pin and when combined with some like primordial weighting strategy. And we can also visualize the dynamic training process of FFP for this high frequency problem. So to effectively resolve such rapid oscillations, we significantly increase the feature dimensions of the RFF mapping, which means we expand the numbers of the nonlinear basis functions. We increase the hyperparameter D in the RFF mapping. During the visualization, we can observe that the IFF pin exhibit the common learning behavior that it still captures the general shape of the high frequency solution very fast in the beginning. In the beginning, it captures the general shape. And subsequently, during the rest stage of the training, the network progressively learned and recovered the sharp oscillations details. So the learning process demonstrates the robustness of IFF framework in overcoming the traditional limitations of the spectrum bias problem. And next, we examine the high-frequency convection equation with a velocity parameter beta equals to 200. So in this scenario, the physical field propagates rapidly over time, resulting in extremely dense wave patterns. You can see like in the exact solution. So the fitting result for all baselines reveals a critical failure mode. Most baselines, including the vanilla pins, the NTK method, and this PIG, they fail to capture the wave propagation, and instead they converge directly into a near zero trivial solution, because I guess it's because the homogeneous the convection function is a homogeneous PDE. But our method successfully avoids the trivial solution trap and accurately capture the high frequency details across the entire domain. So the error map further confirms that the IFF maintains accuracy proving its robustness in solving this complex high frequency physical problems. And finally, we return to the multi-scale convection diffusion equation mentioned at the beginning of the talk. The solution to this equation is a superposition of low frequency and high frequency components. So the result reveals that due to the spectrum bias problem, all baselines method exclusively capture only the smooth low frequency trends of the solution, while completely failing to resolve the high frequency oscillations. But our IFF-ping method is the only framework to capable of simultaneously fitting both frequencies. So these outcomes convincingly demonstrates IFF's performance in modeling coupled multi-scale differential systems. And here is the visualization process. And even for IFF-ping, the early training strategy still learns the low frequency and the smooth component first. But then the visualization shows that how the IFF-ping gradually learn the high frequency during the training process, but not just ignore it as other baselines does. It gradually learned the high frequency from the error plot. We can notice that. So finally, this summary table represents the comparison result across all high frequency and multi-scale scenarios. So based on the average performance of 5 independent experiments per case, it's clearly evident that under this high frequency and multi-scale conditions, all baselines suffered failure most due to the spectrum bias problem, often yielding no meaningful numerical result or just not converge. But IFF-ping and its variants is the only framework that continuously and consistently achieves a precise fitting for all this high frequency and multi-scale problems. And to demonstrate the Fourier-enhanced features, our RFF mapping's ability to mitigate spectrum bias, we designed a challenging multi-scale convection equation with an initial conditions composed of 10 different sine functions of different frequencies and unit amplitude. During the analyze, we compared the performance of vanilla pins against the models where the basis extended with the varying numbers of random Fourier features. So this is the numbers of the D in RFF mapping. And during the training, we carry out one-step solution of the lower level problem for our IFF method. And no additional training for the upper level problem is performed. Because we want to make it an ablation study to show the capacity of to show the capability of the RFF mapping. So for this heat map, we employ the fast Fourier transform to analyze the frequency domain distribution of the network's prediction. So in this heat map, the dark color means the corresponding frequency is learned, while the light color means the frequency is just failed to learn. So from the result clearly illustrates the spectrum bias of vanilla pings, which struggle to accurately capture the high frequency, components. In contrast, for the IFF method, when we gradually increase the numbers of the RFF feature numbers, we can see that it gradually efficiently increased the approximation for different like frequencies. And in the end, we want to further highlight the structural advantages of IFF ping. So we compare it with the well-known the multi-scale Fourier feature method, the MFF method. So MFF method is a very early approach that applies RFF mapping to pings to mitigate the spectrum bias problem. When it comes to the structural comparison between these two methods, MFF follows the conventional logic of RFF application, but just applying multiple RFF mapping directly to the raw input coordinate before they have been sent into the neural network. While effective, the capacity of this feature space I think, is strictly constrained by the hidden layers architecture. So instead of mapping at the input, IFF ping applies the random Fourier feature mapping like gamma D directly after the training of the neural network, after the last hidden layer. So this structural shift is driven by our perspective on the PDE fitting process as a basis function approximation. So because we assume that a larger and more diverse basis function space leads to a better fitting accuracy for the complex PDEs. So by placing RFF mapping after the last hidden layer, we can generate an arbitrary numbers of enhanced extended basis functions regardless of the structure, the width of the network. And also without adding any other like training cost during the backpropagation. This provides a high dimensional and high quality feature sets for the subsequent linear operator solving, like for the QP problem in linear case. So we believe that this significantly boosts the model's expressive power for high frequency and like the multi-scale problem, which increase the approximation result. So this is the comparison for the structure that states why we want to put RFF mapping after the hidden layer, but not between the input and the hidden layers. And the performance across three distinct benchmark further validates our architectural advantages. Although MFF is an RFF-based approach designed to mitigate spectrum bias, its actual fitting accuracy across low frequency, high frequency, and multi-scale problem is significantly inferior to IFF ping. So looking at the specific data, for example, for the high frequency convection case where beta equals to 200, MFF result in substantial relative error of like 3.5 times 10 to the minus 1. So indicating a limited capacity to resolve features under high frequencies. And in contrast, the IFF ping achieves a better performance with 2 orders of magnitude better than MFF. Similar trend can also be observed in the multi-scale scenarios. And in the end, we have some hyperparameter ablation studies. So the most important 2 hyperparameter in our method is the 2 parameter in the RFF mapping, the basis number D and the frequency domain bandwidth sigma. So we evaluate their impact on performance using the low and high frequency Helmholtz equations. The ablation study shows that the too few features maybe reduce the expressivity, while too many features may cause some like overfitting problem, therefore reducing the fitting accuracy. And for sigma, larger value are essential for like especially for the high frequency problems. We can notice that when sigma is 10, then we get the lowest relatively L2 error. But for the low frequency problem, are robust to both hyperparameter, and the high frequency problems are like quite sensitive, especially to the sigma. So this is very coherent with some previous work claiming the RFF mapping to help the neural network to mitigate the spectrum bias. So in the end, we have the conclusion that we propose the IFF ping. We show the novelty through the experiment result, demonstrate that it consistently outperforms some advanced baselines across different scenarios, from low frequency to high frequency to multi-scale problem. And also IFF ping greatly mitigate the spectrum bias problem of pings when capturing the high frequency and multi-scale component during the training process. And also IFFP is quite flexible that we allows the integration with multiple methods during the upper level training. But we also acknowledge that there are some limitations and future works left to do. So the biggest limitation is that it's limited to some complex nonlinear PDEs. So we think a promising direction is to do some like advanced principal bilevel optimization for reshaping the nonlinear lower level problem, so that we can like not make our lower level problem always like stuck or easily stuck into some bad local minimum. And also we want to do some like seriatic analysis to demonstrate that seriatically RFF captures high frequency components in our algorithm. Because we only like from experimental part, we show that it's RFF that helps the method to learn the high frequency component, but we don't do any like seriatic analysis for this RFF mapping after the last hidden layer output. So these are the two biggest limitations. And so this is my talk. So thank you for listening.
Thank you so much, Yulun. Since your slides didn't have number, can you go back to 3 slides before?
3 slides
The
before.
table. No, the table. Yeah.
This table,
Yes.
right? Oh,
Yes.
okay.
What is the optimizer that you are using?
Like for the upper level problem, we are using Adam.
On a double precision setting or single precision?
Sorry?
On a double precision setting, float 64 or float like single precision setting, 32.
You mean this one, this figure, or?
Yeah, I think it should be like single
Yeah.
precision atom.
The floating point arithmetic that you're doing,
Yeah.
is it single precision or double? Probably single precision, isn't it?
Yeah. And also I have like a suggestion for you. I would like the comparison between your method and siren activation function, because
Okay.
I feel like it is doing almost the same thing, and in my experience, it works either better or like the same improvements for this kind of problems with feature layer of Fourier series.
You mean the like to change the activation functions into the sign
To
function?
siren,
Yeah.
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 Yeah, you can try and see.
Okay. Yeah.
Do we have any other questions? Vivek?
Yes.
Yeah.
Hi, Yulin. Very interesting work and talk.
Yeah.
I just have a question. Did you happen to check trying the RFF projection on both the input and the output layers, like what was previously done as well, and after the final layer or the second last layer of the MLP? Did you happen to check that?
You mean like we add the RF layer here?
Yes, and in the end. Because my reason for the question is RFF just at the beginning was better than nothing, and you showed RFF at the end is also better than nothing. So would having one at the beginning and the end help or hurt?
We never tried that, but like for example, like for the MFF method,
Mhm.
after they do the RFF mapping to the input space, maybe they generate maybe like from so originally this hidden layer like just have maybe 64 neurons, but after the RFF mapping in the input space, they get like 200 features.
Okay.
So during the implementation, they also use maybe like 200 neurons in the hidden layers. So they basically increase the numbers of the neurons when training. So yeah, I mean like the reason why we don't want to use the RFF mapping like after the input space is that we don't want to make the network very big. So we don't want to
Right.
add some extra cost. But I guess we can try to just add one RFF layer here, but don't change the size of the neural network.
Understood. Yeah.
Yeah, yeah.
Okay.
I think we can try it. Yeah, thanks.
Thank you. Very interesting.
Thank you.
Do we have any other questions?
Yeah, I have a question, basically to follow up on Nazanin's question. The numbers that you show in terms of errors and the comparisons are good, but it's not, I wouldn't call them state of the art because you're comparing with the Sifan Wangs and so on, which is a little dated. So
You mean
you can get, in fact, there
The table.
yeah, any of the results. In fact, the Berger's equation was pretty bad compared to the state of the art. In Berger's equation for this problem, we get errors of the order of 10 to the minus 8. So I don't know if you've seen our results on 10 to the minus 8 using without any tricks, without any just using double precision and also second order optimizers. So all that, basically you could mitigate. Nazanin said using the siren, which also will have some effect, but really you have to compare with the state of the art. The state of the art today is not what you have as pigs and pin formers and so on. It's really simple, straight vanilla, but with second order optimizers. You get in this table at least 2 to 3 orders of magnitude, 4 for Berger's, lower than what you have. And without any extra cost, turns out, if you implement JAG. So that's kind of where, at least our group, that's what we're doing, and we see these numbers much better. Of course, what you're suggesting is a good idea to move from the input to the last layer where this is effectively the basis. But I'm not sure if you use the second order optimizer, you will actually have any effect, if that will have any effect. So of interest would be here to just take a SOAP. It's a second order optimizer from Google and use it instead of, it's a precondition Adam, and see if you actually get that gain in accuracy due to the extra basis or due to the optimizer.
Okay, thanks. I guess like the reason why is just because the error is not that good because like maybe we're always using the Adam optimizer, and it's because the data set we use. But I would try the second order optimizer and see if we can still get some like better results than the vanilla pins.
Yeah, there is a big difference between like second order and first order optimizer.
Yeah.
Yeah, but also, I don't know, I suggest you to try Siren if it is giving you the same improvement.
Okay. Yeah, I think this like what you said, the siren, I know that, and also for the second order optimizer, we can also combine it with our method because like we are still using the neural network architecture for the upper level training, so we can directly fit it into our method.
But Julian, that's my point. If you use second order optimizer, let's say, do you actually need your method? Because you already have resolved, you have mitigated the spectral bias. That's I don't know the answer to this. I suspect that you don't need it.
Yeah. But it's like just to use the second order optimizer, we can like mitigate the spectrum bias problem even for some very difficult high frequency cases or.
Yeah, it depends on
we're
the
preparing a
optimizer.
paper on that. We're preparing a paper on that. So we have we have results for all these benchmarks that you showed. Yeah.
Okay.
I think Juan has a question.
Okay, Juan, go ahead.
Yeah, hi, Yulub. That was a really nice talk. I just have one short question. Can you go back to the slide when you were showing your architecture, like essentially when you were comparing with Sifan's work?
Which? Which one?
When you were showing when you were showing where you put your feature embedding.
You mean the comparison with MFF
Yeah,
or
No,
yeah, the architecture, the architecture.
the architecture of the whole algorithm or
Oh, the last part of only the
okay,
of
okay. Is that this one
yeah,
or
here this
okay,
one is
okay.
good. Uh, I have one question here. You were saying that in the case, for example, for CFAN, every time that you do the in embedding, for example, you have to do this increasing the dimensions, right? For example, you make the X
Yeah.
and T, and you make 150 features per coordinate, and then you combine them. And also the and you don't have any. How do you deal for the last layer? Maybe that is my question, because if you have 150 features and then you enhance it for X and T, then you get 300. But if in the last layer you have like 128 neurons or something like that, if you do just an enhancement of, let us say, 5, then out
Yeah.
of there you jump all the way to 600 neurons in the last layer, right?
Yeah.
So for the last layer, are you doing something like reducing the number of neurons or something like that?
I mean like from I can show like the so from doing this, like the RFF extension, so here is last hidden layer, and we
Yes.
like do the matrix computation with this random sampling. So
Yeah.
that no matter like how many like neurons we have in the last hidden layer, we can extend it to the 2D basis functions. Yeah,
Yes, so
so
but so you but so you will not have, you're saying that with this approach you will not have that computational overhead of doing feature expansion even if the input dimension is high. That's what you're saying, right?
you mean the computation cost or?
Yeah, when you do feature expansion, essentially you're increasing the number of dimensions, right?
Yes, yes.
Yeah, if I mean, maybe you can see it here in your matrix, the one you're showing, R D times P, right? I assume
Yeah,
that here D is the number of features that you have, the fewer features, right? And
yeah,
P is the number of neurons of the last layer.
yeah, that's right.
Yeah. So when you, for example, when you have inputs, this is cheap, right? Because P is equal to 2, so it's just 2D, the number of the matrix that you're using, right?
Yeah,
But let's say that you want to use a D for the last layer, you have 100 neurons, which is common, right? And
yeah,
that means that your D will be somehow restricted to relatively lower values, like let's say up 10 or 20, because otherwise your last layer is going to explode. It's going to be 10 times 100, and it means that if, technically you have 1,000 features to fit, right?
yeah.
Yeah, so
But
then so since that is the case, my question is, for the last layer, are you making the P smaller, or you're just keeping using the 256 or whatever number you use in the last?
I just keep it for the like for all the baselines method, like the vanilla pins, the NTK method, we just keep the same network size.
But then that will increase the number of training parameters in total, right?
But we don't this like RFF mapping the like parameters is not learnable, so we fix it in the beginning. We just do the matrix computation and we don't need to learn anything.
But the last layer, the linear layer, is not learnable after
Yeah,
because
this layer is
but because because whatever you do in the last part before you go to you have to go to get one single value, right? Whatever
yeah.
you do in the last part. So even if in this part you don't do anything, the last linear layer should be learnable.
Yeah,
And
but
it means,
like for linear PDEs, we can just get a closed form optimal solver so that it's very fast, and no matter like we can have very like high dimensional matrix.
yeah. So, but what will happen for nonlinear PDs?
So yeah, so for like so this is our limitation. So for nonlinear PDEs, we can only do some like using maybe the LBFGS to do the gradient descent.
Yeah, but then the problem is like the number of parameters increases too much.
Yeah,
Yeah, actually, we had some kind of like similar issue because the idea of putting the embedding in the end instead of the beginning. We actually call it like enhanced basis MLP, and we published it like maybe 1 year ago, and it's like part of the cake, and that's the one for one of the networks, and we were using, instead of the Fourier that you're using, you were using Chebyshev. So the idea was like you move it to the end of Chebyshev instead of having the Fourier features, and actually it works quite well. And actually there we also somehow address the Vivek's question about that you can combine both. So we were having like Fourier features in the input, and we have like Chebyshev in the output, and it helped quite well. But I actually was want to pick in your brain because I found that was really interesting what you were doing, and wanted to know how you dealt with the computational cost. Because in our case, what we did is like the last linear layer, the last layer of the neuron, we make it small. So instead, if you have like 200, 200, 200, we made 200,
Yeah.
200, 200. The last one like 20, and then do the expansion, and then do the other part, and that kind of like tackle the problem. But I wanted to know if you're doing something additional than that. So
Okay, but I think it's a very great idea. But we like during our experiment to keep the comparison fair, so we use the same network architecture. But I guess like if you want to like lower the neurons of the last hidden layer, I can try that. But the thing is like for linear problem, we don't need to worry about this linear update because it will not cost many like memories, and the speed is very fast also. But for the nonlinear case, it is something that we need to consider because we can only use like the gradient descent method to do some optimize. So now so now my method is just to, so we don't, for the nonlinear cases, we don't do the lower level update in every epochs, but we do maybe in like every 10 epochs or every like 50 epochs, we find one local minimizer. So that's what I'm doing to reduce the computational cost. Yeah.
okay, that's a nice trick. And also I really like the way you deal with the linear problem. So it was a nice idea.
Okay.
Thank you for sharing.
Yeah, thanks for your idea as well.
Thank you. Do we have any other questions for the speaker? Any comments? Okay, it's time to close the session. Thank you so much, Yulun, for your great talk.
Thank
And
you.
thank you
Thank you.
everybody for joining us today. Have a great weekend. Bye.